In late March 1913, Dayton, Ohio operated as a city built upon deliberate proximity to water. The Great Miami River and its tributaries, the Mad River and Stillwater River, converged directly within the municipal boundaries, their channels confined by engineered levees and crossed by iron bridges supporting streetcar lines and road traffic. Factory whistles marked shift changes at National Cash Register, Barney and Smith Car Company, and dozens of smaller manufacturing plants clustered along the riverbanks where water power and rail transport intersected. Spring rain fell steadily across the Miami Valley, typical weather for the season, darkening the brick facades of downtown buildings and filling the gutters along 3rd Street and Main Street with runoff. The city's relationship with its rivers had been formalized through infrastructure. Levees constructed in the 1860s and reinforced periodically, since then channeled the Great Miami through the urban core. These earthen embankments, faced with stone in critical sections, represented the accepted engineering solution to periodic high water, barriers high enough to contain seasonal flooding while allowing the city to expand into the fertile floodplain. Canal systems built decades earlier still carried barge traffic alongside newer rail lines. Bridges at Main Street, 5th Street, and multiple points downstream supported constant movement. Pedestrians, horse-drawn wagons, electric streetcars running on overhead wires. The infrastructure network functioned as designed, its components interconnected but not consciously redundant. Residents understood flooding as a manageable seasonal phenomenon. High water occurred most springs as snowmelt combined with rain, occasionally requiring sandbagging operations and temporary street closures. Records from the 19th century documented such events without suggesting fundamental vulnerability. The levees had held. The bridges had stood. Industrial operations along the riverfront continued without major disruption. This accumulated experience built confidence not in the absence of flooding, but in the adequacy of the city's response to it. Engineers and municipal officials viewed the river system as adequately constrained, its behavior predictable within known parameters. The geography that made Dayton prosperous, flat land, converging waterways, rail connections to regional markets, created dependencies that remained invisible during normal operation. Power plants drew water from the river to cool steam generators. Gasworks produced illuminating gas from coal, distributing it through underground mains to street lamps and building heating systems. Telephone exchanges connected business districts to residential neighborhoods through copper wire networks strung on wooden poles. Water treatment and distribution relied on pump stations, positioned near river level. These systems operated independently in administrative terms, but occupied the same vulnerable topography, their foundations built to elevation standards based on historical flood records that now represented nearly a century of accumulated observation. As March progressed, rain continued with unusual persistence, but no emergency declarations were issued and no evacuations ordered. The rivers rose within their banks. Factory operations continued. Streetcars maintained their schedules. The infrastructure that shaped daily life in Dayton remained intact and functional, its limitations not yet tested beyond design parameters. The meteorological pattern that developed over the Ohio River Valley in late March 1913 involved multiple low-pressure systems moving slowly eastward from the Great Plains, each depositing moisture across the same geographic area before stalling against the Appalachian highlands. Between March 23 and March 26, rainfall totals across the Miami River basin exceeded 8 to 11 inches in most locations, with some measuring stations recording peaks near 14 inches. This precipitation fell onto ground already saturated from earlier spring rains and, in many upland areas, still partially frozen from winter, conditions that minimized soil absorption and maximized surface runoff. The Great Miami River drainage basin encompasses approximately 5,000 square miles across western Ohio, collecting water from agricultural land, small municipalities, and tributary systems that converge at Dayton. Under normal spring conditions, this basin managed snowmelt and seasonal rainfall through gradual downstream movement, with river levels rising predictably over days as water progressed through the network. The rainfall accumulation of late March delivered water volumes significantly exceeding historical norms within a compressed timeframe. Stream gauges throughout the watershed recorded rising water beginning on March 24, with levels increasing continuously rather than cresting and receding as seasonal patterns typically dictated. Hydrological understanding in 1913 recognized the relationship between precipitation, runoff, and flooding, but lacked the forecasting capability to predict flood magnitude from upstream rainfall data. The U.S. Weather Bureau maintained observation networks and issued general flood warnings, but specific crest predictions and timing remained uncertain. Local officials in Dayton received reports of high water in upland communities, but possessed no method to calculate how those conditions would translate into specific river levels within the city. The information existed in dispersed form, rain gauges showing totals, telegraph reports from upstream towns noting flooded roads, but no synthesis mechanism converted these data points into actionable urban flood predictions. Engineering assumptions that informed levee design and urban development patterns reflected confidence derived from maximum observed flood levels during the preceding decades. The levee system protecting Dayton had been constructed to contain events exceeding previous records by calculated margins, typically several feet. This approach, standard in early 20th century civil engineering, assumed that past maximum flood heights represented reliable indicators of future risk. The rainfall event, now developing across the basin, exceeded the meteorological conditions that had produced those historical flood records, introducing variables outside the design parameters of existing infrastructure. By March 25, rivers throughout the Miami Valley exceeded flood stage. In upstream communities, water covered agricultural bottomlands and low-lying residential areas. The Mad River and Stillwater River, flowing toward their confluence with the Great Miami at Dayton, carried volumes that filled their channels to capacity. Downstream, within the city itself, river levels climbed steadily toward the tops of the levee system. The water carried increased sediment loads, visible as brown discoloration, and moved with greater velocity than seasonal high water typically demonstrated. Surface currents showed turbulence patterns indicating high discharge rates. The precipitation finally diminished during the evening of March 25, but water already present in the drainage system continued moving downstream. The peak flow, the maximum volume of water passing any given point, progressed through the river network according to basin geometry and channel capacity, its arrival at Dayton determined by accumulated rainfall volumes now distributed across hundreds of square miles of watershed. The flood had not yet reached the city, but the water was already in transit, moving through tributary systems toward the confluence point where geography concentrated flow at the urban core. On the morning of March 25, the Great Miami River at Dayton measured approximately 18 feet at the Main Street gauge, approaching but not yet exceeding the height of the levee system. By mid-afternoon, the gauge recorded 22 feet, with water continuing to rise at measurable rates visible to observers monitoring the embankments. The levees, constructed as earthen berms faced with stone and masonry in key sections, extended along both riverbanks through the central city, their crest elevations calculated to provide clearance above the highest previously recorded flood. Water now approached those crest levels, reducing the safety margin to feet rather than the yards that normally separated river surface from levee top. Municipal work crews responded according to established flood protocols, beginning sandbagging operations at vulnerable points where levee height appeared insufficient or where previous repairs had left potentially weak sections. These operations required manual labor, filling cloth sacks with sand or soil, transporting them by wagon to threatened locations, and stacking them to temporarily increase effective levee height. The work proceeded in rain and worsening light as afternoon progressed toward evening, with crews focusing on sections protecting the downtown business district and industrial areas along the riverfront. Water continued rising throughout these efforts, the river surface climbing perceptibly even as sandbag barriers went into place. Seepage became visible along the levee base by late afternoon, appearing as wet spots where groundwater under pressure from the elevated river found paths through the earthen embankment. This phenomenon, understood by engineers as a normal hydraulic effect during high water, indicated that the flood pressure was forcing water through the porous levee structure even without overtopping. Seepage zones typically remained manageable if levee integrity held. Water emerging from the protected side could be channeled away with pumping or drainage ditches. However, sustained seepage could erode material from within the levee, creating voids that weakened the structure and potentially led to rapid failure if the erosion reached critical points. The first overtopping occurred along the North Bank section, protecting the neighborhood known as North Dayton, where levee crest elevation measured lower than sections protecting the commercial core. Water began flowing over the embankment shortly after dark on March 25, initially as a thin sheet spreading across the levee top, before gaining volume and cutting channels through the earthen structure. Once overtopping began, erosion accelerated as flowing water carved away material, widening and deepening the breach points. The process progressed from controlled overflow to uncontrolled structural failure within hours, transforming sections of levee from intact barriers into gaps through which river water poured freely. Throughout the night, additional sections along both the Great Miami and Mad River levee systems experienced similar failures. Some occurred through overtopping where river height exceeded structural capacity. Others developed through internal erosion, where prolonged seepage had undermined embankment stability. The levee system, designed as a continuous barrier, functioned only when intact along its entire length. Breaches in any section allowed water to bypass the remaining intact portions, entering the protected area from multiple points. By dawn on March 26, the levee network that had defined the boundary between river and city no longer functioned as intended. Water moved through and around the barriers, following the natural topography of the valley floor into streets, neighborhoods, and industrial districts built deliberately close to the river for reasons of commerce and power generation. The river gauge at Main Street recorded 29 feet on the morning of March 26, then ceased reporting as the gauge structure became submerged and communication lines failed. This measurement exceeded the previous record by more than 10 feet, surpassing not only the design parameters of the levee system, but also the elevation of first-floor structures throughout the riverfront area. The water carried debris from upstream failures, timber from collapsed structures, uprooted trees, sections of fence and building materials, creating hazards that moved with the current and impacted remaining infrastructure. The flood had transitioned from a confined river event to an uncontrolled inundation of urban space. Water entered Dayton street grid through multiple breach points simultaneously, following the underlying topography that sloped gently toward the river confluence. In the downtown core, flooding began in low-lying districts closest to the riverfront before spreading to commercial streets previously considered safely elevated. The water arrived not as a sudden wave, but as a rising presence, initially filling basements and ground floor spaces before climbing building facades as depth increased. Current velocity varied by location, slow in areas where topography trapped water in pools, faster where gradient directed flow through street corridors toward lower elevations. 3rd Street and Main Street, forming the commercial heart of the city, experienced inundation beginning in the early hours of March 26. Streetcar tracks disappeared beneath brown water carrying suspended sediment. Ground floor storefronts flooded to ceiling level as depth exceeded 10 feet in some blocks. The Callahan Building, Reibold Building, and other downtown office structures became isolated towers surrounded by floodwater, their upper floors remaining dry while first-floor spaces filled completely. Office furniture, store inventories, and business records absorbed water or floated, depending on material properties, drifting against doorways and accumulating in stairwells. The organized commercial landscape dissolved into navigable water surface, marked by building tops and occasional utility poles still standing. Industrial districts along the riverfront sustained immediate and comprehensive flooding. The National Cash Register Complex, employing thousands and occupying multiple buildings near the confluence, flooded to depths exceeding 15 feet. Manufacturing equipment, lathes, presses, assembly machinery, became submerged or stood in water that compromised bearings, electrical components, and precision surfaces. Raw materials inventories absorbed moisture, and finished goods awaiting shipment suffered water damage. Similar conditions affected the Barney and Smith Car Company plant, lumber yards, foundries, and smaller manufacturing operations distributed along both riverbanks. These facilities had located near the water deliberately to access river transport, and in earlier decades, water power. That proximity now translated directly into flood vulnerability. The rail infrastructure connecting Dayton to regional networks experienced multiple simultaneous failures. Rail yards south of downtown, occupying low ground near the Great Miami, flooded completely, submerging locomotives, freight cars, and track switches. The Union Station, serving as the passenger terminal for multiple rail lines, flooded to the platform level, preventing train operations even where track remained passable. Bridge failures compounded these disruptions. The Pennsylvania Railroad Bridge crossing the Great Miami suffered structural damage when debris impact combined with water pressure exceeded design loads. Without functional rail connections, the city lost its primary means of receiving outside assistance and evacuating people or moving critical supplies. Bridge failures occurred throughout the city as flood forces exceeded structural capacity. The Main Street Bridge, a combination vehicular and streetcar crossing, collapsed on March 25 when undermining of pier foundations allowed the structure to shift laterally before sections fell into the current. The 5th Street Bridge remained standing, but became impassable when approaches on both banks flooded. Smaller bridges across the Mad River and Stillwater River experienced similar fates, leaving the city's transportation network fragmented. The bridge collapses removed critical evacuation routes and isolated neighborhoods from rescue efforts, transforming the urban geography into a collection of islands defined by floodwater boundaries rather than by street connections. Power generation ceased as pump stations and generating plants flooded. The Dayton Power and Light Plant, positioned near the river for cooling water access, lost capacity when rising water reached boiler rooms and electrical switchgear. Without electrical generation, streetcar service halted, street lighting failed, and electric pumps that might have managed localized flooding became inoperable. The city transitioned from a mechanically powered urban environment to one depending entirely on manual labor, and whatever steam-powered equipment remained functional above flood levels. This loss occurred not through single-point failure, but through the simultaneous flooding of multiple generating facilities whose combined capacity supported urban operations. Water depth in the most severely affected areas reached 20 feet above street level, measured against building facades and utility poles. This depth submerged first-floor ceilings and reached into second-story windows, creating conditions where only upper floors remaining dry while first-floor spaces filled completely. Office furniture, store inventories, and business records absorbed water or floated, depending on material properties, drifting against doorways and accumulating in stairwells. The organized commercial landscape dissolved into navigable water surface, marked by building tops and occasional utility poles still standing. Industrial districts along the riverfront sustained immediate and comprehensive flooding. The National Cash Register Complex, employing thousands and occupying multiple buildings near the confluence, flooded to depths exceeding 15 feet. Manufacturing equipment, lathes, presses, assembly machinery, became submerged or stood in water that compromised bearings, electrical components, and precision surfaces. Raw materials inventories absorbed moisture, and finished goods awaiting shipment suffered water damage. Similar conditions affected the Barney and Smith Car Company plant, lumber yards, foundries, and smaller manufacturing operations distributed along both riverbanks. These facilities had located near the water deliberately to access river transport, and in earlier decades, water power. That proximity now translated directly into flood vulnerability. The rail infrastructure connecting Dayton to regional networks experienced multiple simultaneous failures. Rail yards south of downtown, occupying low ground near the Great Miami, flooded completely, submerging locomotives, freight cars, and track switches. The Union Station, serving as the passenger terminal for multiple rail lines, flooded to the platform level, preventing train operations even where track remained passable. Bridge failures compounded these disruptions. The Pennsylvania Railroad Bridge crossing the Great Miami suffered structural damage when debris impact combined with water pressure exceeded design loads. Without functional rail connections, the city lost its primary means of receiving outside assistance and evacuating people or moving critical supplies. Bridge failures occurred throughout the city as flood forces exceeded structural capacity. The Main Street Bridge, a combination vehicular and streetcar crossing, collapsed on March 25 when undermining of pier foundations allowed the structure to shift laterally before sections fell into the current. The 5th Street Bridge remained standing, but became impassable when approaches on both banks flooded. Smaller bridges across the Mad River and Stillwater River experienced similar fates, leaving the city's transportation network fragmented. The bridge collapses removed critical evacuation routes and isolated neighborhoods from rescue efforts, transforming the urban geography into a collection of islands defined by floodwater boundaries rather than by street connections. Power generation ceased as pump stations and generating plants flooded. The Dayton Power and Light Plant, positioned near the river for cooling water access, lost capacity when rising water reached boiler rooms and electrical switchgear. Without electrical generation, streetcar service halted, street lighting failed, and electric pumps that might have managed localized flooding became inoperable. The city transitioned from a mechanically powered urban environment to one depending entirely on manual labor, and whatever steam-powered equipment remained functional above flood levels. This loss occurred not through single-point failure, but through the simultaneous flooding of multiple generating facilities whose combined capacity supported urban operations. Water depth in the most severely affected areas reached 20 feet above street level, measured against building facades and utility poles. This depth submerged first-floor ceilings and reached into second-story windows, creating conditions where only upper floors remained dry. The current continued to flow through the city, following paths determined by street alignment and ground elevation, carrying debris that included lumber, barrels, sections of wooden buildings, and occasionally livestock. The sensory environment transformed from urban infrastructure into a slow-moving brown river punctuated by building tops, its surface disturbed by currents and eddies around obstructions. On March 26, as floodwater depth stabilized across central Dayton, fires ignited in multiple locations throughout the inundated area. The ignition sources traced to gas mains that had ruptured when water pressure and ground movement exceeded pipe joint strength. Natural gas, produced at coal gasification plants and distributed through underground cast iron pipes to heat buildings and power street lamps, escaped through fracture points and migrated upward through water, until reaching air at building interiors or upper floors still above flood level. Ignition occurred when this gas encountered pilot lights, open flames in heating stoves, or electrical sparks from failing equipment. Once ignited, the fires burned in structures surrounded by water, fed by continuous gas supply from ruptured mains that remained pressurized. The fire at the Beckel Hotel began during the night of March 26, flames visible from multiple points across the flooded city as the building burned from upper floors downward. Without functioning water pressure in fire suppression systems, and with streets impassable to fire apparatus, no organized firefighting response could reach the structure. The fire consumed the building's timber frame and interior finishes, eventually weakening structural supports until partial collapse occurred. Similar fires developed in residential and commercial buildings across the downtown area, creating scattered points of light visible against the darkness imposed by power outages. The fires burned until fuel exhausted or gas supply interrupted, their spread limited primarily by the water that surrounded each structure and prevented fire from jumping to adjacent buildings. The interaction between flood and fire represented a compound infrastructure failure. The flood disabled fire response capabilities, while simultaneously creating conditions that triggered gas leaks, and the water that prevented fire spread also prevented fire suppression. Building occupants trapped on upper floors by rising water faced the additional hazard of fire burning below them, with escape routes cut off by both flood and flame. Some fires burned for days, visible as smoke plumes rising from points across the submerged city, markers of ongoing destruction that could not be addressed until floodwater receded enough to allow access. Communication systems failed comprehensively during the first 24 hours of flooding. Telephone service depended on exchanges located in downtown buildings, powered by electrical systems now inoperative and connected by copper wire networks where poles had toppled or lines had broken under storm stress. The initial telegraph connections to locations outside the city remained functional briefly before those systems also failed as relay stations flooded or power sources exhausted. By March 27, Dayton existed in effective isolation, unable to request specific assistance, unable to report conditions to state or federal authorities, unable to coordinate internally between neighborhoods separated by impassable floodwater. The darkness imposed by power failure transformed the urban night environment completely. Street lighting, building illumination, and the ambient light produced by urban activity all ceased, leaving only firelight from burning buildings and whatever portable lanterns or candles building occupants could deploy. Navigation through flooded streets became difficult after dark, with boat operators unable to see submerged obstacles or judge current patterns. The absence of light also eliminated visual communication across distances, preventing trapped populations from signaling needs or coordinating movement to rescue points. Food supply disruption became apparent within the first day of flooding. Grocery stores, warehouses, and food distribution facilities in low-lying areas suffered inventory loss through contamination or direct water damage. Commercial food stocks positioned on upper floors or in buildings at higher elevations remained accessible to immediate occupants, but could not be redistributed across the city due to transportation network failure. Without rail connections, no food could arrive from outside sources. Without passable streets, no organized distribution could occur within the city. Building occupants trapped above floodwater levels initially possessed whatever supplies had been present when flooding began, with no means to replenish them and no information about how long conditions would persist. The municipal water supply system ceased operation when pump stations flooded and power failed. Water mains remained intact structurally, but without pressure to drive flow through the distribution network. This failure occurred simultaneously with the presence of contaminated floodwater throughout the city, water unfit for consumption, but present in extraordinary volumes. Building occupants required drinking water, but lacked means to purify the floodwater surrounding them, and had no access to the treated water supply system that would normally provide potable water. Some buildings possessed cisterns or elevated storage tanks containing water reserves, but many did not, creating immediate shortages that would worsen over subsequent days. The isolation extended beyond communication infrastructure to include physical separation between different sections of the city. Neighborhoods north of the Mad River became cut off from the downtown core by both floodwater and bridge failures. The industrial district south of downtown remained separated from residential areas by water too deep for wading and too dangerous for swimming due to current and debris. This fragmentation meant that even with surviving boats or rafts, movement across the city remained difficult and dangerous, limiting the ability of any organized response to reach all affected areas. The city had ceased to function as an integrated system, its component parts isolated by the same water that had entered through the failed levee network. On March 27, as floodwaters began a slow recession from peak levels, military units arrived from outside the affected area to assist with emergency response operations. The Ohio National Guard deployed companies from Columbus and Cincinnati, reaching Dayton by rail lines that remained functional north of the flooded zone. These units arrived with boat equipment, portable field kitchens, and organizational capacity to coordinate rescue efforts across the fragmented city. The military presence provided command structure at a scale matching the disaster's scope, establishing headquarters at higher ground locations that had remained dry and dispatching units to specific districts based on reports assembled from refugees who had escaped flooded areas. Rescue operations prioritized extracting people trapped in buildings surrounded by deep water. Boats moved systematically through flooded streets, checking upper floors and rooftops for survivors needing evacuation. These operations proceeded slowly due to debris hazards, uncertain water depths, and the need to navigate around submerged obstacles including utility poles, overturned vehicles, and collapsed building sections. Boat crews ferried rescued individuals to designated collection points at the flood margin, where receiving stations provided immediate food, water, and medical assessment. The volume of people requiring evacuation exceeded available boat capacity, requiring multiple days to reach all occupied buildings within the flood zone. Bridge construction became an immediate priority to reconnect separated sections of the city. Engineer units assembled temporary military bridges at key crossing points where permanent structures had failed. These installations used pontoon sections or timber trestle designs capable of rapid deployment, providing pedestrian and light vehicle capacity rather than full structural replacement. The Soldiers Bridge, constructed across the Great Miami River at a downtown crossing point, opened to foot traffic on March 29, establishing the first reliable connection between north and south sections of the city since the flooding began. Similar temporary crossings followed at other critical locations, gradually restoring circulation routes through the urban area. Food distribution operations established supply chains connecting railheads at dry ground with distribution points accessible to affected populations. Relief agencies, including the American Red Cross, established field operations, managing donated supplies arriving from unaffected cities. These supplies required physical transport into recently flooded areas, proceeding by wagon once floodwater receded enough to expose street surfaces. Distribution points operated as controlled access facilities where heads of households received rations calculated by family size. The system prioritized efficiency over comfort, focusing on caloric adequacy rather than dietary variety. Bread, canned goods, and staple commodities formed the core supplies, chosen for stability under field conditions and ease of distribution. Water supply restoration involved both infrastructure repair and temporary measures to provide potable water while treatment facilities remained compromised. Engineer units established water purification stations using portable filtration and chemical treatment equipment, drawing source water from wells or protected surface sources outside the contaminated flood zone. These stations produced drinking water at volumes sufficient for human consumption, but inadequate for washing or sanitation needs. Water distribution occurred through tank wagons that delivered to neighborhood points where residents collected allotments in personal containers. This system persisted for weeks as permanent infrastructure underwent repair and disinfection. Medical facilities operated under emergency conditions, handling trauma injuries, waterborne illness, and complications from extended exposure to floodwater. The main hospital facilities had remained functional but overwhelmed by case volume exceeding normal capacity. Field hospitals established in requisition buildings provided additional treatment space, staffed by medical personnel from military units and volunteer doctors arriving from unaffected regions. Priority cases included crush injuries from building collapses, infections from contact with contaminated water, and respiratory illness from exposure. The medical response operated on triage principles, categorizing casualties by severity and allocating limited resources to cases where intervention offered greatest survival benefit. Communication restoration began with military field telephone systems, providing basic connectivity between command posts and operational units. These temporary networks operated on portable equipment independent of the compromised civilian infrastructure, establishing voice communication capacity weeks before permanent telephone service restoration. Telegraph service resumed more quickly, as line repairs could proceed incrementally, and stations required only limited power from portable generators. The first telegraph messages from Dayton to outside locations transmitted on March 28, ending the complete isolation and allowing specific resource requests rather than general appeals for assistance. The organizational challenge centered on coordinating multiple responding agencies with overlapping jurisdictions and limited communication. Military units operated under federal authority. Municipal officials retained nominal control of city functions. State agencies deployed resources under separate command structures. Relief organizations maintained independent operational chains. A coordinating committee assembled representatives from these entities, meeting daily to share information and negotiate resource allocation. This structure functioned through necessity rather than formal authority, maintaining effectiveness through pragmatic compromise as individual agencies recognized that uncoordinated action would produce inefficiency all parties wished to avoid. Floodwater receded gradually during the first week of April, exposing damage that had accumulated during the period of inundation. Streets reappeared as muddy channels filled with deposited sediment, their surfaces irregular where pavement had lifted or where scour had removed base material. Building interiors retained water in basements and ground floors even as exterior levels dropped, requiring pumping operations that proceeded building by building as portable pump equipment became available. The brown sediment left by receding water coated everything it had touched: walls, floors, machinery, inventory, with a layer requiring removal before damage assessment could determine what might be salvaged versus what required replacement. Downtown commercial buildings stood intact structurally but compromised functionally. Water damage had destroyed ground floor contents comprehensively while leaving upper floors largely untouched, creating an inversion where the most valuable commercial space suffered complete loss while less accessible areas remained serviceable. Business owners returning to flooded buildings found paper records dissolved to pulp, wooden furniture swollen and split, metal fixtures corroded by days of immersion. The damage pattern was remarkably consistent across affected structures: total below the high water mark, minimal above it, creating a clear boundary line visible on every building facade. Industrial facilities faced longer recovery timelines than commercial buildings due to equipment complexity. Manufacturing machinery required complete disassembly for cleaning, drying, and inspection before operational capacity could be restored. Precision equipment that had been submerged for days sustained damage from sediment intrusion and corrosion that rendered components unusable even after cleaning. Some plants determined that equipment replacement cost less than restoration of flooded machinery, particularly where technological advancement had made pre-flood equipment somewhat obsolete. The National Cash Register Complex resumed partial operations within months, but required over a year for complete recovery of pre-flood production capacity. Infrastructure reconstruction proceeded according to priority hierarchies determined by system interdependencies. Electrical power required functional generating capacity plus distribution networks, both of which needed repair before service restoration. Repair crews worked outward from undamaged sections, reconnecting neighborhoods sequentially as line repairs and equipment replacement allowed. Rail service resumed on trunk lines first, allowing supply deliveries to the region before branch lines and yard facilities underwent complete restoration. Bridge replacement proceeded as engineering resources became available, with temporary structures giving way to permanent spans designed to improved standards reflecting flood experience. The economic impact extended beyond physical damage to include business disruption costs and population loss. Factories that ceased operations during flooding lost production time, market share, and competitive position relative to manufacturers in unaffected locations. Retail businesses that served daily needs lost customer bases as populations relocated temporarily or permanently to other cities. Some businesses never reopened, their owners lacking capital to fund reconstruction or determining that relocation offered better prospects than remaining in a demonstrably flood-vulnerable location. The city's population declined measurably as residents left, some briefly for the duration of recovery operations, others permanently, reducing the economic base that would support future municipal operations. The catastrophic failure of the levee system prompted fundamental reconsideration of flood control philosophy across Ohio and other flood-prone regions. The concept that emerged, subsequently implemented through the Miami Conservancy District, approached flooding as a basin-wide problem requiring regional rather than local solutions. Rather than attempting to protect cities with barriers that confined rivers to narrow channels, the new approach involved constructing upstream detention basins that would store floodwater temporarily, reducing peak flows at downstream urban areas. This strategy accepted that floods could not be prevented, but argued they could be managed through distributed storage capacity throughout the watershed. The Miami Conservancy District, established by state legislation in 1915, represented a novel institutional structure that crossed municipal boundaries and possessed authority to construct facilities throughout the Great Miami River Basin. The district designed and built 5 earthen dams at strategic locations in the watershed, creating detention basins with combined capacity to store sufficient water volume to prevent repetition of 1913 flood levels at Dayton. These dams operated as dry structures during normal conditions, holding no permanent pools, but designed to capture and temporarily store water during major flood events. The system became operational in the early 1920s, fundamentally altering the hydraulic behavior of the river system without requiring continuous maintenance of stored water. By 1915, Dayton had substantially recovered physical functionality, buildings repaired, utilities restored, businesses reopened. The recovery process had required extraordinary external assistance, billions in economic loss by contemporary valuation, and permanent alteration of the urban economy. The city that emerged from reconstruction looked physically similar to its pre-flood configuration, but operated under different assumptions about its relationship with the river system. The levees within the city were not rebuilt to pre-flood design. Instead, reliance shifted to the upstream detention system that would prevent water from reaching levels requiring levee protection. The Great Miami River continued flowing through Dayton, constrained within channels that remained largely unchanged in position from 1913. The water moved past industrial sites, beneath rebuilt bridges, through the confluence where geography concentrated tributary flows as it had always done. The infrastructure that lined the banks and crossed the channels operated under knowledge derived from failure, understanding that the river's capacity to escape engineered constraints exceeded previous estimation, and that urban systems built within floodplains required protection measures extending far beyond the city's borders. The river remained essential to the city's geographic identity, but it was no longer trusted to remain within the boundaries assigned to it by local infrastructure alone.